I'll recapture the share. All right, so this is Math 317 Operations Research. This is lecture, I think, 10. If not 10, it's lecture 9. Lecture 10, okay. And so, here we go. Okay, so it is not displaying right now. Interesting. Just pause it. Okay, so what I want to do is I want to talk a little bit about, we talked about basic optimal solutions, basic feasible solutions, and then we're going to lead into now the simplex method, which is one of the best ways of solving problems like this. So the cell phone policy is on hold today. You are allowed to use the cell phone if someone is calling you, because I have a guest visiting my next class and I don't want to miss him in case he's having trouble finding the place. All right. For a lot of these methods, all that matters is that we have a way of starting the process, a way of finding an initial solution. And once we find an initial solution, we actually have a mechanism that allows us to go from a guess to a refined guess to a refined guess to a refined guess, and eventually come up with the optimal solution. So a lot of algorithms look at problems this way. You need an initial starting value. The next, of course, is how long is it going to take to search the space? And so a lot of these problems, if you want to come up with the actual solution, if they're real problems with real quantities, it's actually not bad. And we can get real solutions in a very reasonable amount of time. If, however, you are required to solve what's called an integer programming problem, where your possibilities are discrete. Today, we do not have an algorithm that will give us a known procedure to get to an optimal solution in a reasonable amount of time. We can get close, and this is where we use a little bit of the duality. So we saw by looking at the dual problem that if you are close, when you look at the quantity from the dual problem and the original canonical problem, if those two quantities are close to each other, then you're not too far off. So if you're willing to be within maybe 1% or 0.5%, that's not so bad. And for a lot of problems, when you consider the fact that we don't even know exactly what the values of the parameters are for the problem, can you tell me what the demand for Spider-Man 4, if they ever decide to make it, or I've lost track because there's been so many reboots as to what number we on the current franchise. I think it would be 4. I wonder, is it 5 now? Not sure anymore. They've rebooted so many times. But can you tell me what the demand for that movie would be every hour of the day for an 8-week period? No. You can make some reasonable guesses, and you can say, well, this movie is similar to some other movies, and I'm going to look by maybe genre. I'm going to look at, is it a sequel? I'm going to look at, does it have a good song that's being played on the ears? I could look at the time of the year it's being released and try to use this to estimate how its demand might change over time. But there's still going to be guesses. So to be insisting on an optimal solution that's perfect for your values where you're not even convinced that your values are correct. And then later in the semester, we'll talk about, well, what do we do when we're not sure what the values are that we should be putting into the problem? So what I want to talk a little bit now is about how there are some, a lot of problems in mathematics that seem very simple. They give you, methods to do, but to actually extract something from it is not going to be easy. So this is not a class in number theory, but I like to go to number theory as my go-to subject because hopefully a lot of you have seen this and a lot of the material can be explained without too much of background. So is everybody comfortable with what is a prime? So what is the definition of a prime? It's very easy to get this slightly wrong.
Number that's greater than 1.
Good, you put in the greater than 1, yes.
That's only divisible by itself and 1.
Yes, so a lot of people say it's a number that's divisible by 1 in itself. And by that definition, 1 becomes prime. We don't want 1 to be prime, we want 1 to be a unit. This way we have the fundamental theme of arithmetic. Every number can be factored uniquely as a product of primes. So one of the oldest proofs that copyright has long since expired is due to Euclid. There are infinitely many primes. And the proof is very nice. Assume not. So say P1, P2, ... Pn is the entire list of all primes. So let X equal P1, P2, dot, 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 Pn plus 1. So what can you tell me about this number? What are the possibilities? So what are the possibilities? What kind of number could this be? It's an integer, but we're trying to prove that there are infinitely many primes. So what kind of a number could this be? It could be prime or composite. So case 1, X is prime, and that will lead to a contradiction because we assumed our list was complete. So if X happens to be prime, contradiction. So what's the only case that's left? Composite. So case 2, X is composite, which implies there exists a prime P that divides X. That's what it means to be composite. You're divisible by a prime, and you yourself are not prime. Could the prime that divides X be P1? Could X be a multiple of P1? So what would be the remainder if I try to divide X by P1? It would be 1, so it can't be P1. What about P2? Also has remainder 1. In fact, none of these primes can work. So P is not P1, P2, dot, 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 Pn, as all have remainder 1. Therefore, it's a new prime. Contradiction. How many of you have seen this proof before? Okay, so this is a really great example of how to prove things. And so again, what we did is we broke things up into cases. So this is a 300 level math class, but it is a pre-core 300 level math class. You know, if you take real analysis or abstract algebra, you do nothing but proofs all day. So this is a way to help transition into something like this. You know, this proof goes back over 2,000 years. It's beautiful, beautiful proof. What I want to do is I want to try to milk this and try to look at things that you may not have thought of before. Let's actually apply it. You know, it says that there are going to be infinitely many primes. Let's see what we get. Let's see what it generates. So what's the first prime number? 2. So now let's take this method. Let's multiply all the primes, which is on our list, which is just 2, and add 1. We get 3. What can you tell me about 3? It's prime. Let's apply this again. Let's multiply all the numbers on our list. 2 times 3 is? Plus 1 is? It's prime. Let's take all the primes on our list. 2 times 3 times 7. What do we get? Add 1 and you get 43. We have a lot of data points. There's technically 2 cases. What do you think might actually happen? You're looking at this data. What do you think might actually happen? It's okay to be wrong. Well, we know that the list is going to be infinite. Because if we're in either case 1 or case 2, we can generate a new prime. So we know our list is going to be infinite. So we start off in case 1. Then the next time we're in case 1. Then the next time we're in case 1. Then the next time we're in. What do you think might always be true?
The new number's always.
Maybe the new number is always prime. That's not an unreasonable conjecture to make based on this. What would you do to see if this is correct? You've got a conjecture, you always get a prime. So you could try to prove it, or what else could you do? Counterexample. How would you get a counterexample?
Keep looking.
Keep looking. So what should we do next? What's the next multiplication? Yeah, so let me punch up Mathematica. And so what we'll do is we'll multiply 42 by 43 and add 1. 42 times 43 plus 1. Wow, my computer is taking a long time to multiply. So it's 1807. Can you quickly look at that and tell me if it's prime or composite? Or can you at least eliminate certain numbers that it can't be divisible by? It's not divisible by 2,
5.
not divisible by 5, not divisible by 3, because the sum of the digits is not a multiple of 3. It's not divisible by 11. There's a rule for alternating sums of digits. The rule for 7 is a real pain in the ass. But we know that 7 is a multiple of 7. So we just have to look at, is 1800 a multiple of 7? Well, 100 is not a multiple of 7. So I know 18 is not a multiple, so it's not divisible by 7. So we've eliminated all the primes less than or equal to 11. We can keep going. We can, of course, also use the Mathematica command prime q, which just asks, hey, is the number in here prime? And the answer is false. So it does not always become prime. Now what we can do, instead of asking is it prime, we could do factor integer. And so we get, it's 13 times 139. So the very first one we stopped at, I said, we eliminated everything up to 11, 13 happened to be it. And so now, this is where things get interesting. Go back to the screen. So this is called the Euclid-Mullins sequence. So there's a couple of different ways of defining it. So what we do is, as we go through Euclid's method, every time we get a new number, we take the smallest prime number not on our list, and we add that as our next prime. So we already did the 2, 3, 7, 43, and we just saw the next number was 13 times, I think, 139, is that it? 13 times 139. So we would take the 13. Some people do a slightly different version of this where you would take both 13 and 139 as your next two numbers. You take them in increasing order. And then you just keep looking at the sequence. What do you notice about this sequence of integers? I see a smile, which I think is the right expression when you see this. So what do you notice about this?
It gets really large and then fully drop down.
Yeah, it gets really large and drops down. We have these incredibly large numbers here, that it's 107, then an incredibly large number, and then 59. And so there's a lot of questions you can ask about this. So can anybody give me some questions? So when you see data like this, what questions might you ask?
Why is this useful?
One is, why is this useful? What else?
Does it hit all the
Does it hit all the primes? Does it hit all the primes? If yes, can we quantify when? How far do I have to go to guarantee that I get a certain prime? So when you're looking at data in the real world, I want you to get to the habit of asking questions. This is a really interesting sequence to look at. There are some things that we know about this. There's a lot of things we don't. And it takes something which hopefully you'd seen before. Hopefully you have seen in school that there are infinitely many primes, and going from that to then asking questions about how do we find them. So Euclid's method will generate primes, but it may not generate all of them. And the question is, which ones will it miss if it misses any? And if you're going to get a certain one, do you have any idea of how long you have to wait before you find it? You're 31, you're kind of very far down, and just the numbers it's an incredibly difficult sequence to work with. Okay. So let's turn now back to solving linear programming problems. So we've shown if there exists a feasible solution, then there exists a basic feasible. And shown if there exists an optimal solution, then there exists a basic optimal. So for a lot of linear programming problems, it's sufficient to restrict ourselves to looking at a very simple space, the space of basic solutions. Now, for a lot of things, this works well when you have real valued quantities. So if I want to, for instance, talk about how much oil is being produced, is that a real quantity? Or is that like an integer valued quantity? So if you get on the fundamental scale, there's probably discrete steps in terms of how much oil we can produce. When you look at the costs of things, are the costs of things continuous or discrete? Discrete. But for a lot of problems, if the cost is expensive enough, it expands enough orders of magnitude, a few cents difference, you might as well approximate it by something that's continuous. So for a lot of problems that are actually discrete, it's not that big of a deal to replace them as continuous. And so we can set up a lot of problems and just assume that the amount of oil being produced is continuous. We can assume the price is continuous when we're trying to determine things. There are other things that you cannot treat as, quantities that can be divided. Anybody want to give me an example of something that you should not be dividing? There's a nice biblical example. People, right? The Solomon of the two people arguing over a baby. All right, we're going to cut the baby in half, and each person gets half the baby. No, we sell things in units of babies. We don't sell half babies. That's not possible. We can't split something like that. You have a flight, say Boston to Los Angeles. You have to do the entire flight. The plane doesn't just stop halfway through and now is available for something else. So for a lot of things, I either do the flight or I don't. And so for a lot of problems, it's much harder because you don't have that ability to make these small motions. This is the difference between calculus and combinatorics. In calculus, we have functions that are differentiable. And because of that, we have really good algorithms to find maximum and minimum. Check the endpoints and then look for the critical points, the places where the first derivative is 0. For something that is discrete, we don't have that available. And if you think about something like the diet problem, and we say, okay, we've shown that the optimal is at one of the points of intersection, oh dear God. That could be a tremendously large finite set to work with. How do we search through the entire space? So we need really good ways of searching through spaces efficiently. And we're going to talk about various algorithms. Out of curiosity, how many people know Newton's algorithm to find square roots or cube roots? How many people have seen this? This is then definitely something we should definitely have a lecture on. It's one of the simplest algorithms to describe that is also one of the most powerful. It is absolutely amazing. It's what moved me from being a physics major or thinking of going off to physics grad school to going off to math grad school. It's just seeing the power of Newton's method. So we have some basic linear programming problem that we're trying to solve. We're going to look at basic feasible solutions, and from those, we're going to look at basic optimal solutions. And we're going to use something called the simplex method. And the simplex method has two parts. Phase 1, find a basic feasible solution or show none exist. And phase 2, given a basic feasible solution, find a basic optimal or show none exist. Okay, so high level, this is what the simplex method does. 2 steps. Step 1 takes your problem and gives you a basic feasible solution, or says that there's no basic feasible solutions at all. Well, if there's no basic feasible solutions, there are no feasible solutions. And then clearly there's going to be no optimal solution if there's no feasible solution. Step 2, or phase 2, is given a basic feasible solution. So how would we get a basic feasible solution? So we want to run phase 2. How would we get a basic feasible solution?
Just find a solution that is greater than the set, and that satisfies the equation and has any linearly independent.
Okay,
laws.
so how would I get my input basic feasible solution for phase 2? What would I use to get that?
You'd have to use like some kind of algorithm to find one.
Right, is there anything on the board that might give me that algorithm? Yeah, phase 2 requires a basic feasible solution. What would I use to get that basic feasible solution?
Show that a feasible solution exists.
Right, so what would I use to get the input for phase 2? I would use.
A basic feasible.
Right, and where am I getting that from you?
I don't know.
Phase 1,
Okay.
right? There's a reason why this is called phase 1 and this is called phase 2. What is the input for phase 2? A basic feasible solution. How do we get a basic feasible solution? What do we use? So does everyone agree we use phase 1 to get a basic feasible solution? Now, this is where things get interesting. For phase 1, to find a basic feasible solution or to prove that none exist, we use phase 2. What might be problematic about this?
We can't do either phase.
Why not?
Well, it's you're gonna-
Yeah, it looks kind of circular. So phase 2 requires phase 1. And phase 1, it turns out the way we do it, requires phase 2. So at first, when you first read this seems like the most absurd approach possible. But the interesting thing is, you have a little bit of freedom. So we are trying to solve, ax equals b. The components of x are greater than or equal to 0, and we want to minimize C transpose x. That's the canonical problem. Okay. What we can do is we can create a new problem where it's very easy to prove that there exists a basic feasible solution. So find related problem. Where it is clear what a basic feasible solution is. Then use phase 2 here. That gives an optimal basic solution to the new problem, or shows none exist. We choose the constraint so that the optimal solution is a basic feasible to the original. So we're going to go through this in greater detail later, but I want to just give you the overview of what's going on. In order to use phase 2, we need as input a basic feasible solution. We've actually discussed numerous times that there are a lot of problems where it is very easy to give a basic feasible solution or feasible solution. Can somebody give me a problem where you can give me a feasible solution trivially. So give me a problem where it's trivial to find a feasible solution.
Two-dimensional diet problem.
Okay. And how would you get your solution?
Just by checking the intersections.
See, that's a lot. That's work. So you give me two-dimensional diet problem, but just eat a shitload of amount of stuff, right? So much that you'll have enough. But then how much do I have to eat to know that I've made enough? That requires some work. So can you give me a really simple problem where I know I will have a solution?
One-dimensional, where you need to eat a certain amount of something, and you just eat infinitely much of that stuff.
Okay, but I can't eat infinite. So you would.
So like
So I mean, for these problems, you can look at what are your nutrients. Take so much of one product, so long as it has a positive component in each, that you'll get enough nutrients to stay alive. You could do that. Think about owning the airlines. What's your feasible solution?
zero.
Don't fly. You own a movie theater. What's your feasible solution? Don't show movies, right? So for a lot of things, you can come up with a solution. It's going to be a horrible solution, but there's that do nothing solution. So a lot of times it's not a big deal to come up with a feasible solution. For the problem that we care about, we could look at a modified diet problem, maybe, where if you eat too much of something, you die. And now all of a sudden, it's not clear that there is going to be a feasible solution. Imagine, does anybody have a vitamin that they particularly like? Vitamin D, okay, vitamin D. So we must make sure we get a certain amount of vitamin D. And it turns out that the only way we can get vitamin D is lickety-split. They're the only producers in the area of any of a product that has vitamin D. And unfortunately, they only have a very small amount of vitamin D in each scoop of ice cream. So we're going to have to eat massive amounts of ice cream to get the required level of vitamin D. If we have to eat a tremendous amount of ice cream, we might be getting so much of some other stuff that we move into the danger. And there might not actually be a feasible solution to the diet problem, depending on the distribution of quantities that we care about. If we put on there's a maximum amount you can have. So for a lot of real world problems, you're not going to be able to always guarantee that you will be able to find a feasible solution. Okay? For many problems, however, this is not an issue. Right? So for the last few minutes today, I wanted to talk about trying to actually write down some constraints and actually setting up a problem. So let's do the oil problem. And, this might be in the book, but let's imagine we have a couple of refineries. Let's go 1, 2, ... capital R, and we'll label them by lowercase r. And we'll have a bunch of cities. I'll do locations. No, we'll do markets. We'll do markets. We'll have a bunch of markets for the product. And it'll be 1, 2, ... capital M. And I'll use lowercase m as my index for the market. And then maybe each refinery has a capacity. So refinery R has a capacity C sub R. And then what I want to do is I want to ship oil from the refineries to the different markets. Well, the markets will have demands. So market M has demand, maybe D sub M. Okay. And there's one more piece of information I need when I'm trying to decide how to ship oil from the refineries to the markets. What other piece of information might I need? Cost. And I'll do that in green for cost. And then the cost is maybe CRM to ship 1 unit from refinery R to market M. And so I can calculate all these different costs and so on. Now, what do you think might make sense when you're trying to figure out who sends where?
The closest.
Yeah, so maybe the cities that are really close to a refinery, maybe that refinery should be the one that's supplying them. But maybe the refinery doesn't have enough capacity. Or maybe the refinery is not as efficient as some other places. Or maybe some of the other places have, a better cost function. How do you measure how close someone is to another? So what's your metric for how close two places are? No, it's not miles. The metric is how expensive is it to ship. So imagine the Panama Canal is open. Then something on one side of the canal and the other are very close to each other. If the Panama Canal is closed and you have a super tanker, you can't send the super tanker through now. You either have to go all the way around. And we had this, was it the Suez Canal that had the issue a year or so ago? Where all of a sudden, global supply nightmare because a lot of tankers now had to be diverted. It's not how close you are in miles, it's what is the cost. So what do you think some of the constraints might be for this problem? So can anybody think of constraints? Or what should our variables be? So what should the variable? We're trying to figure out how to ship oil.
With a certain cost.
Well, so that's what we're going to try to minimize the cost. But what do you think the variable should be? The variables.
The price of oil.
The price of oil is going to be kind of included with our cost. But what are we trying to do? What's the problem we're trying to solve? Shipping oil from refineries to the markets. So what should our variable be? How many subscripts should X have and what should they be? So CR was the capacity of refinery R, DM was the demand of market M, CR sub M was the cost of sending from refinery R to market M 1 unit of oil. What subscript should I have on X? RM. So this would be the amount of oil sent from refinery R to market M. And that's the variables. And those will clearly be non-negative. Right? Okay, so now that we have that, all right, so here is all of our stuff. So here's our constraints, and here's our definitions. Here's the things we're looking at. And now, what do you think we're trying to minimize? What do you think the objective function is? The cost. So minimize cost. And what is the cost? So it'll be the double sum of the cost of sending a unit oil from R to M times XRM, which is how much oil we're sending from R to M. So R goes from 1 to big R, M goes from 1 to big M. So that's going to be the cost. So for this problem, it's not that hard to figure out what is the cost. Now we have to start doing the constraints. So can somebody give me a constraint? Yes.
Can't ship more than your capacity.
You can't ship more than capacity. So how would we encode that? So in English, cannot ship more than capacity. So for all R, for each refinery, right? I want to have a constraint for each refinery. So for each refinery, I can't ship more than its capacity. Well, I would then just sum M goes from 1 to M of, oops, oh, I don't know how that changed, of XRM. And that would have to be what? So that's how much I'm shipping, because I'm going over all possible markets. So what would this have to be? Less equal to CM. So that is, you can't ship more than your capacity. Can you think of another constraint? So one constraint is you can't ship more.
A market can't receive more than its demand.
Good. Now, there are actually times when you would want to receive more. For instance, you might want to build up a strategic reserve. And so cannot receive more than want. And so now instead of for all R, it would be what? Right. So now it would be for all markets, the sum over all the refineries of how much we ship to that market is at most its demand. So we see that it's actually not that hard to write down constraints for this problem. Is there anything else that we really have to have as a constraint? No. You can't ship more than you have, and you don't receive more than you want. And so we've now set this up. Is this in the form of a canonical linear programming problem? No, why not?
Because it uses summation.
It's not, no, it's not that it uses summation. I can write this in matrix form. It's just one, just all the components are just one. It's not the summation. So for the canonical programming problem, it's what? It's AX equals B. I've got less than or equal to this. So what you can do is you can introduce an extra variable. You have to introduce some extra variables to make it an equality. So if this is strictly less, well, let me just add an extra variable for each R. That's my slack. So basically, if there's any capacity that's not being used, give it to me. Oh, wait a minute. And we said we cannot receive more than we want. Actually, for this one, the constraint should actually be, it should just be equals dm, right? Right? Is we might as well say that you receive exactly what you want. And then, of course, if that's not possible, then there's no feasible solution. That one isn't too bad, but it is possible that we might be under capacity. So what you then do is you just add an extra city. So add extra city that gets leftover capacity. That gets extra capacity. And in fact, just make that extra city the refinery itself, right? And what will be the cost of shipping to yourself? 0. So what you can do is you can add just an extra city, but then you might have to change this a little bit in terms of what its demand is, or maybe you don't care about getting its demand. All right, so this is a good place to stop. So we started to see today how you actually set up the problems that we're looking at. And now in the next class, we'll start figuring out how do we actually solve them.